Okay, so first let's recall the two centers, three centers we have learned. First one is the incenter. Give a triangle. We can draw the three angle bisectors. The important theorem we learned about this is the angle bisectors are concurrent. Mm. Because of this theorem guarantees the existence of a common point. We call this I the incenter. Peter, let's turn on the camera, Peter. We also showed that if we draw perpendicular lines from the incenter, the three sides, the three perpendicular lines, they have the same length. We will call it R to be the radius. Point of concurrence, the incenter. Okay, so because they have the same distance, if we draw a circle centered at I, with radius R, this circle will go through the 3 points. Moreover, by the converse of the tangent line theorem, so we call these 3 points the perpendicular fit. Not only it contains the perpendicular of it. It's also tangent. So because of this, we call this circle is inscribed. That's why we call it the incircle. We have the name incircle, inradius, and incenter. It's because this circle is tangent to the three sides of the triangle. So now, given a triangle, we can draw the incircle. The other direction, if we draw a circle, we draw three tangent lines, we get a triangle. Let's go the other direction. It's kind of the converse of the construction. We start with a circle. And draw three tangent lines. Okay, so with a circle. Then I draw three tangent lines, kind of arbitrary as long as they are not parallel. Okay, let's see our first line. Let's use a different color. Kind of arbitrary. The only requirement is they're not parallel. Okay. So we started with a circle. Let's mark the center of the circle. Then we draw three tangent lines. They're kind of arbitrary. Don't have, you can draw your own lines, don't have to be the same. The point is, if we connect the vertices, okay, let's label the vertex A, B, C. Then we connect it turns out the three segments are the angle bisectors. Okay, so you can see this, you should compare this construction with the previous construction. Previously, we start with a triangle. We draw the angle bisectors, angle bisectors, angle bisectors. We prove they are concurrent, so they intersect at a point. We proved they have the same distance. We can draw a circle, so we have the incircle, inradius, and incenter. Now the other direction is that we start with a circle. We draw three tangent lines. The tangent line to intersect at the 3 points, so we have a triangle ABC. Now we connect vertex with the center with a segment, bisect this angle. We connect the angle vertex to the center, bisect this angle, bisect this angle. Okay, so we can go back and forth from triangle to circle, and from circle to triangle. Okay. Second construction. This is about the center of mass. And it has a more traditional name. It's called the centroid. Okay. So for this one, again, we start with a triangle. Then we find the three median, midpoint, not midpoint, midpoint. The marked midpoint.
Hey,
Yes,
we just go just
Aaron.
a little bit back up. I just wanted to copy everything and I almost missed. Okay.
Okay, maybe you want to very beginning,
Yeah. Okay, yes, perfect.
but that will take a while.
No, it's I'll just write quickly.
Okay, okay. So we start with a triangle.
Uh-huh.
We draw the angle bisectors. We proved that they are concurrent. So they intersect at the common point. We call this point the incenter. We draw perpendicular lines from this point to the three sides. We show that these segments have the same length. So this is called the inradius. We have the same length. If we draw a circle of radius r, then the 3 points are contained on a circle. Moreover, we apply the converse of the tangent line theorem. We show that this circle is tangent to all three sides. This is why we call it the circle is inscribed to the triangle. Inscribed circle in circle.
Yes.
Okay.
Check.
So the other way, so previously we started with the triangle. Now we start with a circle. We draw three tangent lines. Arbitrary, don't have to be the same. You draw any three tangent lines, they intersect the 3 points, we have a triangle.
Yep.
Now if we connect the vertex with the center, this bisect the angle. We connect vertex with the center, this bisect the angle. Connect, it bisects. Okay. Oh, maybe let's think about it. Why? We kind of arbitrary. I just connect the 2 points. Why? It must be the bisector. Amy, any guess? Kind of
Oh.
arbitrary. Why it must be the bisector?
I'm guessing
Okay.
the circle.
Because sorry,
Uh-huh.
because I feel that it will be concurrent that way, right?
Okay. So we will use concurrence. The point is, initially we have a center. We have 3 points. Now I connect them, I connect them. I connect A, B, C to the same point. Of course, it will be concurrent. In particular, pick any point. I connect. These 3 are concurrent, but it's not good enough. Clearly, this one, they are not bisectors. Why are these bisectors? Okay, Aaron, you want to try? Aaron?
Never mind. I was gonna say
Okay.
they bisect the circle, but
So the point is that we have a triangle. We can go over the construction we have before. We draw the angle bisectors. At this moment, we don't know this is the angle bisector. We draw 3 angle bisectors by the previous construction. We know they are concurrent, and their intersection point is the incenter. This is the incenter, so there must be the angle bisectors. Why? Because I is the incenter. The incenter is the intersection of the angle bisectors. So this is the reason why. Okay, so I is the incenter. It's the intersection of the angle bisectors that we have over there. Incenter angle bisectors. So therefore, they are angle bisectors. Okay. Second construction, last time we call it center of mass, but this is also known as centroid. It's the intersection, mark the midpoint of the 3 sides. Draw the median. Oops, not good. call this G. So the theorem about this okay. Okay. Many of you have the camera off. Let me remind you to turn on the camera. Okay. Peter, let's turn on the camera. The Fred, let's turn on the camera. Okay. The three. So we call it G, the point of concurrency. So this is the centroid. Okay. So this one, there's no circle about it. It's just the center of mass. It's kind of from related to physics. The third center. Third center is called the circumcenter. We should compare this with incenter. We compare the circle. Compared with incircle. Compare circumradius. In radius. Okay, so what is the circumcenter? Again, we start with a triangle. We will mark the midpoints as we have done before. So previous, we mark the midpoints, we connect vertex, midpoint, midpoint, vertex, we connect them. This time, we mark the midpoints. Instead of connecting, we draw the perpendicular lines. So we call these lines the perpendicular bisectors. Okay, so let's mark the midpoint. About here. This one is about here. Approximate. Then we draw perpendicular lines. Hopefully it's not that off. Draw perpendicular line. Draw a perpendicular line. Okay, not bad. Okay, then our theorem.
On
Yes,
the line,
Aaron.
I think you should move that bisector node up on the AC.
What's that? I'm sorry.
I think you should move the bisector node up on AC.
Okay, okay. So you mean this one?
Yeah,
You think this one, they have different lengths?
slightly, just a little up.
Okay, let's take this. It's a little bit off because I just approximately correct.
Oh,
Because if this may be not that accurate. This may be not very accurate. This may be not very accurate. The point is they are concurrent. If you have this, I'm happy with it. Okay, so to convince you, I'm going to mark this as perpendicular theorem. Perpendicular. Bisectors are concurrent. Okay. Now let's see why. It appears to be for this triangle, they are concurrent. But why is true for all triangles? Okay, let's go back to the previous constructions. This one, why are the angle bisectors concurrent? How did we prove them? Fred, any memory about this? Why they are concurrent? Jessica, what about you? Do you remember the proof? Angle bisectors are concurrent. And Amy, an idea? How did we prove this?
It was like the one really long homework that
Oh,
you gave us, right?
okay, yes. So in that homework, we have several steps. We started with two angle bisectors. They intersect at a point. Then we connect this with the third one. We proved this is the angle bisector. Therefore, the three are concurrent. Okay. Started with two. Draw the third one. Prove it is a angle bisector. A lot of steps, but that's the main idea. Okay, second one. Let's see how we prove this one. Why are the medians concurrent? How do we prove this one? Aaron, any memory about this? Why?
that was like last time or something.
Okay, yes, that's correct. Last time. This one a little bit tricky. So again, we started with two of them. Let's see this median and this median. We proved that this median partition this median into the ratio 2, 1. Okay, the two lines, they intersect. And this intersection point partition the median the ratio 2, 1. By the same argument, this median also partition the line is the ratio 2, 1. So the both partitions have the same ratio. So the intersection point, this one and this one, they must be the same. So they intersect at the same point. We proved that this median and this median, they partition this third median into the same ratio. The intersection point must be the same. Okay, now let's go to here, prove why. Okay, to prepare ourselves for the proof, we will state a very simple fact. Give a segment. Draw the perpendicular bisector. Of segment, let's see, BC. Okay, I will recreate the picture. I have a segment here. I will find the midpoint, draw the bisector. Okay, it's about right. Then for any point on the bisector, we have PB equals PC. These two segments okay, let's think about it. Why? Why they have the same length?
Oh,
Mhm.
Pythagorean theorem.
Okay, Pythagorean theorem. We have a right triangle, so PB square is the summation of the two squares. PC square, summation of the two squares. Common segment, midpoint, the squares are the same. Okay, so proof, I will just write down the Pythagorean theorem and you can fill in the details. Okay. Now the second direction. Second direction. Draw a perpendicular line. Of BC. Let P be a point. If PB equals to PC, then P first is the perpendicular bisector. Okay, let's draw a picture. B, C. This time I draw an arbitrary perpendicular line. It doesn't have to be the, I don't know if it is. I just draw a perpendicular line. Pick a point. If its two segments have the same length, then it must be the perpendicular bisector. Okay, why? Why it must be the perpendicular bisector if these two have the same length?
PB and PC are the heights of the triangle.
PB, PC, you mean height?
Yeah, like the three lines that make the triangle concurrent, and then this line here, the P line thing. No,
This line.
yes,
Okay, let's call this line L. Okay.
yeah,
Mm-hmm.
and then it bisects the triangle itself. That's inside the circle.
Okay. Let me think about how to argue this. Okay, we want to show that it's the perpendicular bisector. Okay, Akira, you want to say something? Yeah.
So basically, if you think of it as two right triangles, if PB and PC are the same, and P and the middle point, P to the middle point of L where it intersects BC is always going to be the same. So if PB and PC are the same, then that squared plus the P to the middle point's M. So that PB squared plus M squared is going to be equal to PC squared plus M squared, which is going to be equal to. Wait, no.
Almost.
I got confused.
Yeah, almost.
Squared. Well, no, PB squared is gonna be equal to MB squared times plus M squared, and also PC squared is gonna be MC squared plus B squared.
Mm-hmm.
Plus.
Okay. Yes. Okay. I got it. Okay. So the point. So this again the Pythagorean theorem. We want to prove that it's the perpendicular bisector. We want to check these two segments have the same length. By the Pythagorean theorem, BM squared is the difference of the two squares. CM squared, the difference of these two squares. Common side, same square, so these two must be the same. Midpoint, bisector. So again, Pythagorean theorem. Okay, I will skip the details. Now we are ready for the proof of the theorem. Okay, let's recreate the, let me draw proof of the theorem. We have a triangle, and we have three perpendicular bisectors. Okay. So I will start with a perpendicular bisector, another perpendicular bisector. I call this point D. I call the intersection point O. Okay, so the steps mark two midpoints. D and E. Draw two perpendicular bisectors. Suppose they intersect at O. At O is the intersection point. The third one, we draw perpendicular line. From O to the BC. Okay, so be very careful this time. We draw a perpendicular line. Unlike the previous two, they are perpendicular bisectors. At this moment, we only know it's perpendicular. We don't know, and we want to check if this is the bisector. Okay. Want to check. Oh, let's mark this point, P. Okay, if we can verify this, then this is the angle perpendicular bisector, perpendicular bisector, perpendicular bisector. They all go through the common point, so they are concurrent. So this is the missing piece. And how can we verify this? We know it's perpendicular. The y must be the bisector. Okay, we will use the two facts we stated before. Given a perpendicular bisector, the distance to the two vertices are the same. If the distance to the vertices are the same for some point on the perpendicular line, then this line must be the perpendicular bisector. Okay, so now we are ready to prove. Let's connect the three vertices. Connect, connect, and connect. Proof. OA, OB, OC. Okay, first, I wanted to see that OA equals OB.
Question.
Yes,
Why would you call OP the perpendicular bisector of the two others?
you mean here?
Yeah, you said the, but
Uh-huh.
the others.
Okay, so okay, that's a very good point because I didn't think something I said implicitly of BC. Is it better now?
Yep.
Yes, I'm missing some information missing over there. They perpendicular bisector of this side. But this one, we have perpendicular bisector, perpendicular bisector. The only missing piece is this one. Okay, I claim OA equals OB. Why? Amy,
Because of the concurrency. Wait, no, I didn't mean concurrency. No, they're not concurrent. Because like D is perpendicular and they're bisectors. Yeah.
because this is the perpendicular bisector, and for any point on the bisector, the distance to the two vertices are the same. So this is the perpendicular bisector, and O is a point on the perpendicular bisector. The distances are the same. Okay, so we checked. Next, I claim OA is also OC. Why? OA, OC. Why are they the same? Jessica, what do you think?
I think they're the same, because the center, I don't know.
Okay, so here we have this. Jessica, for any point on the perpendicular bisector, the distances are the same. So we will apply this again to this angle bisector. I'm not angle, perpendicular bisector. O is a point on the perpendicular bisector. The distances to the two vertices must be the same. So the same fact. Combine the two, I want to see OB equals OC. OB equals OC. Okay, let's see why. Kira, do you have a guess why?
Well, OA equals OB and OA equals OC, so OB will equal OC.
Okay, yes, because they both equal to the same term, they must be the same size. Now, let's check this one. If distance on a perpendicular line to the two vertices are the same, then this line is a perpendicular bisector. We verified this is perpendicular, and OB equals OC. We conclude it must be the perpendicular bisector. Not enough space. We started with two perpendicular bisectors. We draw a perpendicular line from an intersection point. It turns out this line is also a perpendicular bisector. Therefore, the three perpendicular bisectors are concurrent. Again, this is of BC. Okay, we will have 5 minutes break. We will resume at 8:28. We have a break.
Okay.
Okay, so our theorem, the three perpendicular bisectors of the triangle ABC are concurrent. How did we prove this? We started with two of them, two perpendicular bisectors. They intersect at a point O, then we draw the perpendicular line from O to the third side. We verified OA equals OB, OA equals OC. Therefore, OB equals OC. Being perpendicular, it turns out this one is also the perpendicular bisector. So all three perpendicular bisectors go through the point O. They are concurrent. Okay. So we finish the proof, the point of concurrence.
I have a question.
Yes.
Since you're teaching us geometry, I have a question. Is there like any, say, case where this might be useful in a real life scenario?
It will be very useful. Yes. I'm not sure how real you want to be, but it's kind of real in math.
Okay.
Point of concurrence. I will tell you one interesting application. Okay. A very special fact, what we verified is the distance from O to all three vertices are the same, OA, OB, and OC. We call this radius R. To distinguish it from the previous one, the I, R, this one I will capital R, the capital letter, point of concurrency. OA equals OB equals OC. We call it R. Now we draw the circle. Centered at O with radius R. Okay, let's see what happens. I'm going to make a copy of the graph. Hopefully I can do it quickly. It's not that easy because I have to go between pages. Make a copy. I got this. Paste. Okay, nice. Okay, so at this stage, we don't need the perpendicular bisectors. I'm going to erase them because there are too many lines kind of distracting. I'm going to erase this. Oh, sorry. Okay, now we have O. This is our radius R, R, R. So if we draw the circle center at O with radius R, it will go through the 3 points A, B, C. Let's see if I can draw this nicely. Okay, too large. Let's make
That's
it
kind of
smaller.
inaccurate.
Huh?
That's kind of inaccurate, I hate to say.
It's not easy. Not easy. Let me see can I change this, make it more accurate. Um, okay, not bad. Aaron, right?
Sure.
Okay, so we draw the circle center at O with radius R because the distances from the center, the 3 vertices equal to R. So this circle contains the 3 vertices. We can compare this circle with the incircle. Let's see the difference. I'm going to make a copy of this to make a comparison. Copy, cut. And I go to here. I put them together side by side. We'll see the difference. Okay, I'm going to remove the extra lines that we no longer needed. And let's try to draw the circle. This circle is I'm going to try to draw a better circle here. Okay, so this, the incircle is inscribed to the triangle. So it's tangent to the 3 sides. Yes, Kira.
I just have a question. When you say O is the point of concurrency, O is the point, what's like the point of concurrency of what?
Of the 3 perpendicular bisectors.
Oh.
So I erase it. Now you don't wait. Yes, that's why we have a different picture here. the perpendicular bisector, perpendicular bisector, perpendicular bisector, they are concurrent, and O is the point of concurrency.
Okay.
Okay, after this, I erased this because it's too many lines. So I erase it here. Still, this is the point of concurrency of the three perpendicular bisector. Maybe I can sublimate here. Of perpendicular bisectors. Okay, so this circle goes through the vertices and it contains the triangle. The triangle contains this circle. So we call this circle circumscribed. Okay, because of these two properties, this one is called the incircle. So this one is called the circumscribed, circumcircle. Circle. And this one, the center is called the incenter. So O is called circumcenter. And R the in radius. So here, this capital R circumradius. Okay, we can compare the two circles of same triangle. One contains all 3 points circumscribed to the triangle from circumcircle, circumcenter, circumradius. And this one,
Question?
yes,
Why are there so many circums?
yeah. So we could say O is the center of the circumcircle. R is the radius of the circumcircle. But here we want to emphasize these two are the properties of the triangle. As we have done here, we have so many yin.
That's
So
because
this
there is
is
a
the
triangle. Is it because there is a triangle?
yes. Okay. Another missing piece for this one, not only we locate the center, we also have a formula for the in radius. Who remember the formula? How do you find the in radius? Okay, I'm going to give some hint. It'll be the square root.
Yeah, oh yeah. Square root of s minus a times s minus b times s minus c or something like that.
Oh, and
Over
yes,
s.
s minus a, s minus b, s minus c over s. It's the same as the area over s.
Half perimeter.
Over the half parameter, yes. Okay, here we have another radius. Again, we can find the formula for this radius. Not easy.
I think I might know.
Yes.
Is it ABC over 4A?
ABC over 4 capital A, the area.
Uh-huh.
So this is the same ABC using the here formula. Okay. In this with the homework, I will give you some hint and you will derive the formula yourself. Okay, so don't worry about it. It will be our homework. We will with some hint. Okay, so this is the third center. The last one. Last one is called the orthocenter. O-R-T-H-O. Oh,
Question?
yes,
What's our altitude?
the height.
Extended?
You will see what it means. There are two cases. Okay. So the first case, we have an acute triangle. A, B, C. The altitude is the height of the triangle. Let's draw a perpendicular line. This is the one altitude. Let's draw another perpendicular line. This perpendicular is about
Right angle? Okay.
Let's draw a perpendicular line. Not yet. Okay, this is perpendicular. From each vertex, we draw a perpendicular line. This is called the height, also known as the altitude. Okay, now you can guess what our theorem is.
Concurrent.
It turns out, yes, the three altitudes. Okay, now let's see how do we prove this? Why? So my triangle is, let me see if I can scale to make it smaller.
Hold on. Does this work on obtuse triangles?
Okay, so let's do this one first, and then we'll check that one later. Want to check if I can make it smaller.
Junction point.
Okay, now I cannot move. Let's move this. We need a little bit of extra space. Okay, to prove this, there are different ways to prove it. Is a straightforward way. I'm going to draw parallel lines through each vertex. I will draw a parallel line parallel to this side. This vertex, I draw parallel line parallel to this side. This vertex, I will draw a parallel line parallel to this vertex, parallel to this side. Okay, I'm going to draw 3 parallel lines. I'll use different color. Okay, maybe I have made it longer. Through this point, I draw another parallel line. Through point C, I draw a parallel line to AB. Okay, so now we are ready to prove the theorem. Draw.
That's basically like a circumcircle, right? But it's just a triangle.
Yes, kind of. Yeah, kind of. Parallel lines through the 3 vertices. Okay, they intersect. I will mark the intersection point. I call this E. Call this F. Call this G. Okay, now let me ask you, if these 2 lines are parallel, this is perpendicular to BC. What can we say about this line to FG?
It should be perpendicular to GF as well.
Okay, this will also be perpendicular.
Uh-huh.
What about, let's see, this one? It's perpendicular to AC. What about this?
It's also
EG.
perpendicular. Because
Okay, another perpendicular.
are parallel.
Another perpendicular. Because it's perpendicular to the parallel one, it's perpendicular to this one. Okay. Next. Let me think about it. Perpendicular. Okay, so these 2 lines perpendicular. These 2 lines perpendicular. What can we see about these 2 segments? I want to say they have, okay, Amy.
Oh, wait. I was gonna say they were equal.
Okay, correct. Okay, because we have this give us a parallelogram. The 2 sides have same length.
Are they cyclic?
No, not yet. They just a parallelogram. Okay, Aaron, what about these 2 segments?
They're also equal because it's parallel.
Okay, because this is the parallelogram, also equal. Okay, AG. equals BC, AF equals BC. What can we say about AG and AF?
They are also equal. So
Okay.
A is the midpoint of G.
Nice. Okay, I'm going to write down the conclusion. I will let you fill in the steps. Step 1. A is the midpoint of FG.
Or GF.
GF. Okay, that also works. We also know I'm going to call this point. I have so many points. I want to label this maybe X, Y, Z. Okay, X, Y, Z. We also verified AX perpendicular to FG. Okay. What is this line called? Is the name for this?
Orthocenter?
No, this line. This line is perpendicular and bisector. So this is the perpendicular bisector of FG. Okay, so AX is the perpendicular bisector of FG. Okay, next one. I claim BG equals AC. Okay. Also, BE equals AC. Therefore, BE equals BG. So B is the midpoint. Of EG. We also know that the BY perpendicular to EG. It turns out this is also okay. Now you know the game. I claim CE equal to CF. Anyone tell me why? Amy, any guesses? Why they must be the same?
It's like basically the same reasoning as how A and AG and AF are equal.
Because this one they equal to the common segment. These two, they also equal to the common segment because of parallelogram. Okay. So C is the midpoint of EF. Same argument, similar conclusions. Of EF CZ perpendicular to EF we get another perpendicular bisector. Perpendicular bisector of EF. All right. Now what do we have? We have that these three lines, they are the altitudes of a triangle ABC, but they are also the perpendicular bisectors of a triangle EFG. Now we apply our previous theorem. Our previous theorem, the perpendicular bisectors are concurrent. Okay, so these three lines, they are the perpendicular bisectors of EFG. They must be concurrent. Okay, so the AX, BY, CZ are the perpendicular bisectors of triangle EFG. So by our previous theorem, perpendicular bisectors are concurrent. Okay, let's see, how did we prove this? Why they must be perpendicular? Because they can be realized as the perpendicular bisectors of a larger triangle. And we verified before the perpendicular bisectors are concurrent. So they are concurrent. They are also the altitude of the smaller triangle. So the altitude of this triangle are also concurrent. Okay, so this completes the proof. Okay, let me